Hi, welcome to my humble little chemistry show. Okay, if you haven't met me already, I'm Doug. Yep, that's me. All right. Well, hey. Anyway, this is neat. This is kind of cool. You haven't heard of atomic orbitals. Maybe you haven't heard of all of that. And if you haven't heard of that, maybe you haven't heard of molecular orbitals either. But hey, look, I've got this thing here. Sometimes you will have. Let me move up here a little bit. Sometimes you might have, I don't know, let's say these little, these atoms. You got an atom over here and they decide to hook up, but when they hook up, what they don't discover is one of them's greedy. They find these things always out later, right? And it takes all the electrons, right? And when it takes all the electrons to itself, guess what happens? This side becomes a little bit more positive, and this side becomes a little bit more negative. And actually a lot in terms of, well, depending on the atom, of course, too. So we draw a little line through it, kind of like this, and we call that the dipole moment. And what that means is this has just created a tiny little magnet the minute they hooked up. That's cool, tiny magnets. So some of the things you might not have considered to be, excuse me, some of the substances that you may not have considered to be magnetic actually are on a certain level. Sometimes you just need a powerful magnet to notice it. Here's a case in point. You can take liquid oxygen and a magnet will attract it. Okay. Now, let's see why that's the case. Okay. We know positives and negatives attract, right? So we'd expect that maybe something negatively charged here and something that looks wrong. This wasn't supposed to, this is supposed to be negative, right? Okay. We would expect something negatively charged to attract something positive, right? Something positively charged to attract something negative, and that's really how a salt sticks together. So let's take a look at how it works at the molecular orbital level. Okay. I'm assuming at this point that you've already looked a little bit at electron orbitals for individual atoms. So if some of the things I say here confuse you, you can go look up on Khan Academy. There's some great videos about how electron orbitals are filled. All right, here's how it works. I've got this happy little O2 molecule. Okay. Well, an O2 molecule is actually two oxygen molecules. No surprises there. We know that. Duh. Oh man, did I really? Okay, hang tight for a sec here. This is a silly little housekeeping thing, but I really don't want to break this picture, so because I'm going to use it again. So go up a layer. Yeah, here we go. All right. So this is an O2 molecule, and this is an oxygen atom, and this is an oxygen atom. Those two things make up that one O2, right? Now, what do we know about oxygen? Well, it's in group 6, right? And so that means it's got 2 open spots for electrons, right? Or it's got 6 valence electrons, is another way of saying that. Let's see what that looks like filling in. We already know that the 1s orbital is going to be filled because we're so far into the table, and only hydrogen and helium. Well, that's once you get past that, you're there. So what I want to do is I want to start filling in the electrons from each of these on their own side. If you can kind of imagine a tiny little, I don't know, like a fence right down the middle here, and we're going to load them up as they fill in. So in the 2s orbital for oxygen, I know that I'm going to have 1 and 2. It's full, right? And that's true for the other oxygen too, because they're exactly the same oxygen. So I take those down here and I start counting the total of this side. I don't want that to look like a, well, here. I'm going to total this side, and I'm going to total this side, and count them from the bottom up to fill these orbitals. But here's what it means. You see this one says S2? No surprise, that's your 2s orbital, right? But this is a molecular orbital. Half of it is the bonding side, and the other half of it is the anti-bonding. And you'll see these diagrams in a whole bunch of different shapes, but usually something like this little star here or an asterisk will denote that this is the anti-bonding side and this is the bonding side. And what happens if they're both full is there is no magnetism. We say that it would be diamagnetic. Okay, that means diamagnet. But if you have a pair of magnets, it's paramagnetic. Okay, that's how I'm going to remember. So 1, 2, 3, 4. Count them in. 1, 2, 3, 4, right? Okay. And this next one right here, well, I've still got, I said there were 6, right? I've got 4 left. So let's count them in. 1, 2, 3, 4. Hun's rule, right? 1, 2, 3, 4. And now I'm going to count them in from the bottom up. 1, 2, 3, 4. Did I count that right? Oh yeah, but there are 2 of them, right? This always messes me up. You know, it's probably better if you just add them together. You say, oh, 4 on this side, 4 on this side, and fill in the 8. 1, 2, 3, 4, 5, 6, 7, 8, and you're done. Okay, what does this tell me? Well, these empty spaces here, let me highlight them, okay? These empty spaces here, oh, good grief, that's terrible. But it'll work. And this empty space here and this empty space here, right? Those are the anti-bonding spaces, right? You see the star? So that means this is going to be paramagnetic, right? Because it's going to attract paramagnetic. Okay? Now, let's try it again. I'm going to save it here so I can get some memory freed up. Let's try another diagram. Okay? Let's say I have, this time, a slightly different one, and I don't want to make it exactly the same, so I'm going to go, how do I want to do this? Let's say it's a nitrogen, okay? It's a nitrogen 2, but it's not just any old nitrogen 2, it's a nitrogen 2 negative. In other words, it's got 2 extra electrons. Okay. In fact, yeah, no, let's go crazy. Okay, we're going to say it's a nitrogen 2 negative, 4 negative. Let's say that. Okay, 4 negative. All right, this is where I always got screwed up, so I hope this will help. We're going to fill them in again, right? Now, nitrogen in the first level, we know it's exactly the same, right? So I fill those in. That takes care of my first 2 on each side, right? Okay, so how many would normally be in nitrogen? 5 valence electrons. That takes care of 2, but I've got 2 more on each side, right? Because this would be an N2 minus, and this would be an N2 minus. Like how I worked that out? Okay, is that hard to read? Let's just be kind, because I don't want to confuse anybody, least of all myself. Okay, so now I have these ions on both sides, and I can count them in. This will be the nitrogen. Okay, I said 5. That's 1, 2, 5, and then 6 and 7, right? So this is going to be more like a fluorine than anything. So 1, 2, 3, 4, 5. That's 2, 6, 7. Okay. 1, 2, 3, 4. 5 plus 2, sorry, is 7. I had like a flashback to class where I got stuck on this very same thing, and apparently it was a traumatizing moment for Mormon. moment for me. Traumatizing Mormon. Okay, anyway, yeah, here we go. Now I need to count those in, but I'm not going to do it the hard way this time. I've got 1, 2, 3, 4, 5 on each side. That means I've got 10 to count in, right? So let's start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that is still paramagnetic. Let's make sure I counted those right. 2, 4, 6, 8, 10. Yeah, I really wish I had made that stronger. Okay, because what I wasn't counting is, you know, I wanted another 2 here. How would I do that? How could I make this a diamagnetic molecule? Well, not that this is likely to happen, but I guess I could make it in 1, 2, 3. Yeah, if I made this, if I made this a 3, if I made this a 3, and I end up here with a 6, right? Then I can go like this. Now that would not be attracted by a magnet. Okay, so that is it. That's molecular orbitals. Once you understand that the bonding and the anti-bonding, if they're all full, they repel, and that's diamagnetic, and you understand that if there's anything empty, it's paramagnets, then you're good to go. Hope that helps. Bye.